All right, classwork's on the board, page 318, doing numbers 7 through 12. You're finding the first derivative, and then once you found the first derivative of each function, find the second derivative as well. Take just a few minutes to work on these. Pause the video while you do, and when you're finished, go ahead and resume the video. All right, well, let's take a look at numbers 7 through 12. Number 7, what was the first derivative of f of x? Jamie?
2x plus 2.
Good, f prime of x is 2x plus 2, and then f double prime of x, the second derivative,
2.
just 2. Number 8, Quentin, what'd you get for the first derivative?
4x plus 5.
Good, 4x plus 5, and then the second derivative,
4.
4. Number 9, Jamie, the first derivative?
2x minus 3.
2x negative 3, and then the second derivative,
2.
2. Notice all three of those, the second derivative is constant. We're going to look at that at the end of the hour today. Number 10, what is the first derivative? Quentin?
6x squared minus 14x plus 4.
6x squared minus 14x plus 4, and then the second derivative, Quentin?
12x minus 14.
12x negative 14 is correct. Number 11, Jamie, what did you get for the first derivative?
12x squared plus 6.
12x squared plus 6, and the second derivative?
24x.
24x is correct. Number 12, Quentin, the first derivative?
27x squared minus 4x plus 6.
Good, 27x squared negative 4x positive 6, and the second derivative?
54x minus 4.
54x negative 4 is correct. Questions on first and second derivatives. Feel really easy at this point, doesn't it? I mean, for all the scare that you had earlier, now it's super easy. We also used these derivatives to find physics things and functions, to find physicsy things. We said that as an object moves, at whatever rate it moves, the longer it keeps moving, the farther it will get. Distance, then, is a function of time, and so we can write distance as a function of time with the notation d of t. T being time, d of t being the distance it travels. So we said d of t is distance or displacement, might be an even better way to look at it, but we'll stick with the less physicsy term here. Distance or displacement would be measured in meters, typically, represented by the letter m. We said if we were to take the first derivative of distance, that would be taking the first derivative of this function compared to the change in time, the limit as the change in time approaches 0. Well, that first derivative is going to give me what, Jamie?
The velocity.
Specifically the
Instantaneous.
instantaneous velocity. Average velocity, just find a change in distance over a change in time. But if that change in time is approaching 0, like the first derivative limit does, then that's going to be not just velocity, but instantaneous. Hold on. Instantaneous velocity. And we measure velocity in general in what units?
Meters per second.
Meters per second. All right, and then if we were to take the derivative of that, the second derivative then of the distance time function, that would give us what, Quentin?
Acceleration.
Specifically? Instantaneous acceleration. I'm going to abbreviate here because I am lazy. Instantaneous acceleration. Because remember, the second derivative is simply the derivative of the first. The change in d prime of t over change in time. Change in velocity over change in time is acceleration, but again, it's a derivative because the limit is that that change in time is approaching 0. So it's not just acceleration, but instantaneous acceleration, where acceleration in general measured in meters per second squared. Again, if you are in physics like these students are, those units are easy to remember. If you're not in physics, you may have to make sure you commit those units to memory. Your homework was on page 316, so flip back just a page. And we didn't do what the directions said to do. We did our own thing. And we said on page 316, numbers 2 and 4, you are going to find the distance that the object will have traveled after 2 seconds have elapsed. Then you were supposed to find the velocity at that 2-second point. The instant it hits the 2-second mark, exactly how fast is it traveling at that instant. And then also, how rapidly is the object accelerating right at the 2-second mark. So you were given the distance time function, and again, not all movement, as I mentioned in our last lesson, is describable in terms of a function. But if motion can be described by a function, then we can use the function and the derivatives to find these things. So how far did the object travel total after 2 seconds had elapsed? Jamie?
8 meters.
8 meters. You're simply finding d of 2, and that is 8 meters. Good to go on that. Then I said the velocity at exactly 2 seconds. So literally we're trying to find what, Quentin?
D prime.
D prime of 2. But you can't find d prime of 2 until you first find d prime of t. So we need to find that first derivative first. And what is d prime of t?
2t plus 1.
2t plus 1. So the d prime of 2 becomes 5. And since it's instantaneous velocity, we'll say 5.
Meters per second.
So after 2 seconds have elapsed, it's gone 8 meters. By the way, 8 meters in 2 seconds is what? Average velocity. 4 meters per second. But at this precise instant, it's going 5, which clearly means it's speeding up as it's moving. So what is the acceleration at the 2 second mark? Well, to find acceleration, we need the
The second derivative.
second derivative. So we need to first find d double prime of t, Jamie, which is just
2.
2, and that tells us as we find d double prime of 2, though it'd be d double prime of anything, it's a constant acceleration at
2 meters per second squared.
2 meters per second squared. So every second it's getting 2 meters per second faster and faster. Again, the average acceleration would be, hey, it's going 5 meters per second. After 2 seconds, average acceleration, you might say, well, it's 2.5 meters per second squared or something, but, or well, it's going from 0 to 5, I guess, would be, yeah. Let's see, it's not the 0th instant. How fast was it going? D prime is 0. Right at the 0 mark, how fast was it already going?
1.
So it was literally moving forward. This is, I guess, not unlike, for instance, okay, be honest. You sit at the red light, and kind of watching the lights on the side, and they go green, yellow, red, 1,000, 2,000, and you actually hit the gas just before the light turns green. You ever done that? As long as there's not a police officer around. But at the 0th mark, this guy's already moving forward, okay? So if we were finding average acceleration, we could say, okay, in 2 seconds, what's the change in velocity
4.
per unit time? Well, that's 2 seconds that have elapsed. That gives us an average velocity of 2. The same as the instantaneous, right? But that's because it's constant acceleration smoothly at 2 meters per second squared. Again, you didn't have to find some of the other things. We were looking for 8 meters for the distance, 5 meters per second for the instantaneous velocity, and 2 meters per second squared for the instantaneous acceleration. How did we do on number 2? All right, let's take a look at number 4, and a different function this time. What is the function, Jamie?
It's d of t equals negative 0.5 t cubed plus 2t squared minus 1.
That?
Mm-hmm.
All right, and we need to find how far has it gone after 2 seconds have elapsed. We need to find d of 2. And Quentin, what did you get for your answer?
11.
Well, that's not what I got. Jamie, what did you got?
I have 6.6 meters.
Uh-oh. I might be wrong, but one of you is also wrong. Let's see here. So cube the 2. 8, right? Times negative half.
Okay.
Negative 4. We also have a negative 1, so total that's negative 5. Keep that number in your mind. 2 squared
4.
times 2. So we have an 8, and we have a negative 5. 3 meters. So I should have had 3 meters for our answer there. Be careful with the calculator. In this case, it almost feels like it's easier without the calculator, doesn't it? Just kind of keeping track of it. But yeah, negative 0.5, or 0.5 negative, times 2 cubed, plus parentheses, 2 times 2 squared, close parentheses, minus 1 equals. It's probably faster to do in your head. The number 2 wasn't a hard one to work with there. Anyway, we move on. We want the velocity at 2 seconds. That means, class, we need to find the d prime, the first derivative. What is the first derivative, Jamie?
Negative 1.5 t squared plus 4t.
All right, and so d prime of 2, let's see if we can do this in our heads. We square the 2.
4.
Times negative 1.5, or maybe we would use a calculator for that.
Negative 6.
Negative 6, he didn't need a calculator, and then 4 times 2.
8.
So we have negative 6 and positive 8.
2.
So 2 meters per second at the 2 second mark. Do we have that correct? Okay, yes.
I see what I did. I forgot the negative.
Lost the negative, so it didn't copy the negative, so hence all the answers changed. That's where you got,
That's where I got my 11, I think.
yes, that would have been 11. Okay, yeah, that would have been 11 if you didn't have the negative. And then for the next one, 14? Okay, all right, and then d double prime. T. We need for the second derivative, for the instantaneous acceleration, d double prime t class.
Negative 3t plus 4.
And you would have had just plain old 3t plus 4. All right, so what the instantaneous acceleration at 2 seconds should have been, Jamie?
Negative 2 raised to second squared.
Now that's interesting. And Quentin, you would have had something obscene like 10 meters per second squared, which is faster than gravity. That's really interesting. After 2 seconds have elapsed, it's gone a total of 3 meters. At the 2 second mark, its movement is forward 2 meters per second, but the acceleration is negative. Do you remember what negative acceleration is from physics? It's slowing down. So it started off fast and it's slowing down at this instant. So it had been going faster than 2 meters per second, but it's been slowing down, gone a total of 3 meters. Some interesting stuff here we can conclude from this. Again, do you have to do all the other conclusions? No. But, you know, hey, I like to tie the physics in a little bit here. Questions on this? All right. Close your books for just a little bit. We may get back to them, we may not, depends on time. And let me give you another classwork problem to practice with this. Let's suppose we have an object that travels according to this function. D of t is equal to 0.7t squared minus 3t plus 1. I want you to find the total distance traveled after 4 seconds have elapsed. I want you to find the velocity right at the 3 second mark. And I want you to find the acceleration at the 2 second mark. Take just a few minutes to work these problems. If you're finished, let's take a look at this. If you're not finished, pause the video because my students in here are finished with this. To find the distance after 4 seconds, what do we do, Jamie?
We plug in the 4 for the t's.
Yeah, just find d of 4. And what did you end up getting for your answer? I just realized I'm not going to be able to do this in my head very effectively.
0.2 meters.
That's not very much at all. But you are right, 0.2 meters. So 4 seconds have elapsed, and it's only gone 0.2 meters. Part of me really wants to see the breakdown of the movement on this thing. We might do that in a moment. Then I want the velocity at 3 seconds, which means I need to first find
d prime t.
the first derivative, right? And the first derivative is...
1.4t minus 3.
So at the 3 second mark, how fast is it going?
1.2 meters per second.
It's going 1.2 meters per second. So after 4 seconds, it's only gone 2 meters. This is very strange movement. And then the d prime of 3 is 1.2 meters per second. And then we want the acceleration at 2 seconds, Jamie. That means we need to find the second derivative, d double prime of t. And what is that second derivative?
1.4.
1.4. And so d double prime of 2 is
1.4 minus the second squared.
So, I mean, the object is accelerating. Maybe it started at a huge deficit. So I'm really curious here. Let's find d of t and t here. And let's kind of map it out over the first 4 seconds, because I'm really curious. No seconds, 1 second, 2 second, 3 second, 4 seconds. With no time elapsed, where's the object? It's already at a 1 meter head start. At 1 second, ooh, that's why. At 1 second, how far has it gone?
Negative 1.3.
I'm getting a negative 1.3 meters also. So notice, in that first second, it's actually gone backwards 2.3 meters total, right? It was a meter ahead, and it moves all the way back to 1.3 meters behind whatever starting position we have. So it takes a big movement backwards. At 2 seconds...
Negative 8.2.
Really? That doesn't sound right. I'm negative 2.2. Is that what you said? Or did you say negative 8.2?
Said negative 8.2.
Should be negative 2.2.
Rather than negative 2.0.
2 squared times 0.7 minus 6.
What did you do?
Minus 12.
Oh, okay, you squared the 2 again. Gotcha, okay. So yeah, we got negative 2.2. So in the second, by the end of the second, it's actually moved even further back. So in that 1 to 2 second window, it keeps on moving further back. It's moved another 0.9 meters backward. But at the third second, where is it?
Negative 1.7.
So man, that's okay. I was expecting a little bit more forward movement than that. So at the third second, it's gone a half a meter back toward the starting line, but it's still not even back to starting position. And at the end of the fourth second, well, we already found it. It's 0.2 meters. So at the end of the fourth second, this object has moved almost 2 full meters forward. Now it's just across the starting line by 0.2 meters. So big shift, very quick, by the way, very quick backward movement. Little bit more backward movement, but slower. Little bit of forward movement slowly, and then a rapid movement forward. Which makes sense then, at the 3 second mark, it starts moving forward rapidly to get there. And at the 2 second mark, it's starting to pick up some steam because it's going back forward again. So the 2 second mark is kind of its furthest point back, presumably, starting to move forward again and slightly speeding up. So I'm curious what its velocity would be at the 4 second mark. Let's find d prime of 4. What's its velocity at the 4 second mark?
2.6.
2 ways to find this. The most conventional way is right here, plug in the 4, right? The other way is if it's going to accelerate 1.4 meters every second, meters per second squared, add it on to get you 2.6. So the next one is going to be 4. And the next one's going to be 5.6. So each second getting faster and faster. Because that's a constant acceleration all the way through. How does that reconcile with the velocity? Let's find the velocity at d prime of 1. D prime of 1, it's moving backwards.
Negative 1.6.
Negative 1.6 meters per second. I mean, technically, d prime of 0, that's an easy one.
Negative 3.
So right at the start, so this is like cars going uphill and they're like a stick shift, and right at the 0, wait, I'm going back, right? Moving backward and just trying to, okay, I'm not going backward as quickly, I'm going backward less quickly, I'm starting to go forward finally. So slowing down in the backward movement, but yeah, interesting, really interesting movement here. Being described. Again, I'm a nut for physics, so indulge me here. There is another application to derivatives, though, changing gears in my Notes, gears, get it? Stick shift. Anyway, I need to stop. I need more sleep. Another application of derivatives is graphing, right? Kind of comes full circle here with this concept of analytic geometry, right? Where analytic geometry was designed to allow us to quickly and easily graph graphs. But in some respects, the analytic geometry didn't help a lot. Now, for conics, we had a lot of methods we could use. For other things, we had intercept, symmetry, domain, and range. But remember the cubics? The cubic equations were kind of awkward to try to figure out. I mean, it did some funny stuff, a little squiggle, and then you get into quartic equations, they do even weirder stuff. Man, trying to analyze those with intercept, symmetry, domain, and range is really a limitation. But there is something interesting that you can use for non-linear functions, and it's this idea of critical points. So next section of your notes, graphing with critical points. Graphing with critical points. Now, this form of graphing you're going to like because it's rough sketches. It's not nitpicky details, right, Jamie? It's not nitpicky details of perfect accuracy. It's all about just getting a rough sketch. And in a large sense, engineering is not about nitpicky details necessarily at the initial stages, but getting the rough idea. You can always fine-tune later, but you got to make sure the rough idea is accurate. So that's where critical points come in. For instance, if I know I've got a single critical point here. A critical point, by the way, write this definition. A critical point is the point on a curve where the slope of the tangent equals 0. A critical point. It's the point on a curve where the slope of the tangent equals 0. The point on a curve where the slope of the tangent equals 0. For instance, take a parabola. Notice the slope. It's going up, 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 a la, roller coaster. And then right here, the tangent slope would be a 0. It's positive, positive, steeper, positive, right? You got all these positives going up. Less positive, less positive, less positive. Right here, where it changes direction. Jot that down. It's where the curve changes direction. Put that in parentheses. Where a curve changes direction. Now the slope is 0. Steep, positive, still steep, less steep, very shallow, 0. Because right after this, the slopes immediately start going down with negative slopes. But at the critical point, it changes from being a positive to being a negative. And right there, the slope is 0. If I know this is the only critical point, I don't know exactly how my parabola is shaped. But I know it's either that or it's that. Make sense? Now, if my critical point has positives on both sides of it, then maybe that, it would have to actually fully come in like that. But this would still be positives all the way across, but at that moment it goes to 0, but it's a consistent positive throughout. Well, that's different than a negative slope changing to a positive or a positive changing to a negative. So knowing critical points can tell me quite a bit about the curve. That's why we're going to use critical points. So to find critical, by the way, one quick note too. Remember we said sometimes your cubics do goofy things like this? Well, we can have a couple critical points in the same curve, right? Because right here, positive slope going up, 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 0 negative slopes, 0 again, positive slopes, right? So even those funny looking cubic equations, you can have a couple critical points. I do want to point this out, by the way. If a critical point is at the bottom of the curve, it's called a minimum point. If it's at the top of the curve, it's called the maximum point. This would be neither minimum nor maximum because it's just in the middle of the curve. Here, we would have what's called a local maximum. It's not the highest point of the curve. This is the highest point of this curve. This is the highest point of this part of the curve. This is the lowest point of this part of the curve. It would be called a local minimum. Okay? And so determining not just what are the critical points, are they minimums, are they maximums, things like that are going to help us to be able to graph. So to find critical points, step number 1, set f prime of x equal to 0. To find critical points, step number 1, set f prime of x equal to 0. Set f prime of x equal to 0, because after all, what is f prime of x, class?
Y.
The first derivative. Now f of x is y. F prime of x is the first derivative, and the first derivative is the slope of the tangent line. So if the slope of the tangent is 0, set f prime of x equal to 0. Does that seem very incredibly logical? All right, this will give you the x values of the critical point. This will give you the x values of the critical points. So step number 1, f prime of x, has to equal 0. But that's only an x value of a critical point. That's not a point. A point has an x and a y, or an x and an f of x, right? We tend to think y is, we've been graphing with x and y since 9th grade. So step number 2 then, to get the, quote, y values, plug into f of x. And I'm not sure why I did a cursive f right there. Quentin, bad influence. Plug into f of x to get the y values. And I'll put that in quotation marks because technically they're f of x values, but it's easier to think of them as y values. So we get some x values at critical points, so the logical thing to do next is we plug into f of x to get the y values. So you actually know the critical point, or points, x and y, abscissa ordinate. You could actually plot it. For instance, we're going to come back to our notes in just a moment, but let's suppose we had this function. F of x is equal to x squared minus 4x plus 2. And I want to know, I know that's a parabola, but where is the vertex? Where are the critical points? Well, in Algebra 2, we had a way to find it. In pre-calculus, earlier in the year, we had a way to find it just a few weeks ago. But the fastest way to find it is to find the first derivative, which would be
2x minus 4.
And set that equal to 0, and get x is equal to 2. Add the 4, divide by 2, boom. I have the x value. Then we need to plug that back into f of x and find f of 2. Negative 2. 4 minus 8 plus 2 is negative 2. There's the x, there's the y value. So what is my critical point?
2 negative 2.
Boom. Much faster than anything we've been able to do before. And that's why calculus is something that was sought after. There's a side of everyone's like, we already had like math, like arithmetic and numbers and stuff, and I see the value of that. But once we got to algebra, it's like, why? Okay, I start to see the value in algebra. Geometry, okay, I see the value. Calculus, why couldn't they just stop? Because they were lazy. And by coming up with calculus, we actually come up with faster ways to get things done. I know 2, negative 2 is my critical point. So a quick sketch graph, 1, 2, 1, 1, 2, let's try to use roughly the same size units. This is where my critical point is now. Is it maximum or minimum? Well, going back in your mind to Algebra 2, since it's a positive right here, the graph is going to go up. So we remember from Algebra 2, but what about other graphs that aren't parabolas, that we don't know as much about? The way you're going to determine algebra or mathematically whether or not this is a minimum or a maximum is to see what the slope is doing. Remember, we said if this is a minimum point, you're going to have negative slopes coming in, going down, and you're going to get positive slopes going out. A minimum point trends to be positive. Negative, less negative, less negative, less negative, less negative, 0, little bit positive, more positive, right? It trends toward becoming positive at a minimum point. At a maximum point, it's positive slope, less positive, a little bit positive, very little positive, 0. And then a little bit negative, more negative, more negative, more negative, more negative. At a maximum point, the slope tends to become more and more negative. Does that make sense? So if we can see what the slope is doing, how the, catch this phrase, the slope is changing around my critical point, how the slope, first derivative, is changing, second derivative. The second derivative tells me the behavior of the slope. First derivative gives me the slope. Of course, I said I want the slope to be 0. You show me where the slope is 0. But the second derivative will tell me how the slope is changing. So step number 3, find f double prime of x to see how the slope is changing. At these points. So the first derivative is used to get the x value, or x values. F of x is used to get the y value, or values that go with those. But the second derivative describes the behavior of the slope at the critical point. So here's your f prime of x. Let's find f double prime of x. And of course, class, f double prime of x is just 2. Consistent, constant changing of the slope. Not constant slope, a constant change in the slope. It constantly gets more positive. If it constantly gets more positive, that means that therefore we must have a minimum point. So my graph in some way comes down and goes back up. Now, how wide is it? I don't know. Okay, that's where the other side, that's where earlier material could tell us if we cared about that. But I at least know the point's going to be right here, and it's going to go up from there. We can worry about other stuff later, but this at least gives me a very quick, rough sketch of what my graph will look like. Questions on this? Let's do just a few of these together in the time that we have remaining. Write this down. And by the way, you will not need graph paper for this. You're welcome to use graph paper, but because we're doing rough sketches, we can just sketch those on our regular paper. Though, I mean, you only got, what, a couple weeks left? Got a lot of graph paper left, you want to use it up? Let's do this. All right, so I'll write this function down. F of x is equal to negative x squared, positive 6x, negative 1. I don't want to know the exact details of the graph, but I want a rough sketch of the graph. And the quickest, easiest way to get a rough sketch of the graph is to find the critical points. Because a critical point is anywhere the slope turns into a 0. Anywhere the slope of that tangent line or the slope of the curve becomes 0. So to find the slope, we would need the first derivative. And if I know the slope is supposed to be 0, I simply set the first derivative equal to 0. What is the first derivative, Quentin?
Negative 2x plus 6. Negative
2x plus 6. And I'm going to set that first derivative equal to 0. Well, if negative 2x plus 6 equals 0, what is x equal?
3.
Positive 3. Probably the best way is to send the 2x over as a positive, right? And divide away the 2. It doesn't really matter. X is 3. 1 critical point, correct? The critical point is going to be 3 something. But Jamie, just knowing it's 3 something doesn't help. I want to know where the point is. I need to know not just abscissa, but also ordinate. I need to know y value, or better yet, I need to know the f of x value. So we go back to f of x for a moment, and we find f of 3, the x value we just found. And f of 3, Jamie, is 8. So apparently 3, 8 is my critical point. So far, so good? Now I need to figure out what the slope is doing. Again, if you remember from Algebra 2 that a leading negative means it goes down, you already know this is a maximum point. But let's assume we don't remember that, or we just want to practice the process, which is really what we're doing. To figure out how the slope is changing, we need, class, the second derivative. So I now need to find f double prime of x. And what is f double prime of x, Quentin?
Negative 2.
-2. Now, normally I would find f double prime of 3 specifically. How is it behaving at my 3? But since it's a constant, of course it's just going to still be -2. This means the slope tends to go negatively, which means it must start positive, going up, it hits a 0, and then it goes down. If it goes down from my critical point, then that means this must be a maximum. So, our quick sketch, over 3, up 8, and the graph is going to go down. Now, again, how wide is it? I don't know, but that's a rough sketch of what my graph would look like. And we're done. Questions on that? Write this one down. Let's go with a cubic now. because parabolas are boring and too easy because we studied them so much in earlier years. Let's go with something we didn't study much. G of x equals x cubed minus 3x. If I want to get a quick sketch graph, the first thing I need to do, Jamie? First derivative, because I want to find, or I want to do what with my first derivative?
Find the x value, or the critical point?
The critical points, and we're going to get a critical point wherever the
x value changes.
I'm going to get a critical point anywhere the slope is
0.
0. So I'm going to get a critical point anywhere the first derivative equals 0. What's the first derivative, Jamie?
3x squared minus 3.
And we're going to set that equal to 0. Now, not surprisingly, class, that's a quadratic, which means I'm going to get 2 x values, 2 critical points, not 1. Easy enough? All right, so for my 2 critical points, I need to solve this incomplete or pure quadratic.
Positive negative 1.
Good. We're going to add the 3, divide the 3, take the square root. X is equal to both positive and negative 1, which means 2 critical points. One is an x value of 1, one's an x value of negative 1. Both cases, I need to know the ordinates, the y values. Quentin, what do I do?
Plug in the g of x.
Plug into g of x. So we're going to go here, and we're going to find g of 1, and I'm going to find g of negative 1. What is g of 1, Quentin?
-2.
And g of negative 1?
3.
Well, you cube a negative 1,
-1.
negative 1. Negative 3 times negative 1,
+3.
3, and negative 1, 2. All right, now it doesn't always work out nice symmetric like that. 1, -2, -1, 2. It has happened to in this particular instance. So those are my 2 critical points. But I want to know which one's max, which one's min. Or surely they're not both maximums, right? That shouldn't be able to work, right? So to figure out whether they're maximum or minimum points, class, we're going to find the second derivative. I'm going to find
g double
prime of x. And that's going to be?
6x.
Now, for each critical point, it's going to do its own behavior. Notice this is variable fluctuation here. It's not a constant change like we went with a parabola. Line has constant slope. Parabola has constant change of slope. Cubics are going to have variable changes of slope. So I'm going to say, okay, well, what is the behavior of the slope, second derivative, when x is a 1? What do I get? 6. Now that's positive. If you have a positive change, the slope tends to go positively from that point. So that means it must go into the point negatively, going down, hit the point at a 0, and then go up from there. It's a minimum. So if you want to memorize, positive means minimum, negative means maximum. I tend to think that's opposite of intuitive, right? I would think positive would be max, negative would be min. So just think it's always the opposite. A positive means it's a minimum point because the slope is going up from there. So this, now it's not the minimum, it's a local minimum because the graph is going to go to infinity. And then for g prime, double prime of negative 1, I assume a maximum. And of course, g double prime of negative 1 class. And since it's negative, again, that means the slope tends to, from this point, go downward, comes in going up, goes to 0, then goes down. Yes, indeed, it is a maximum. And so when we set up our graph, I've got a point at 1, -2, that's a minimum. And I've got a point at -1, +2. That's a maximum. So the graph goes down from here, and it goes up from here. Well, in between, you can see that there's going to be this connection, and then it just keeps going up, and keeps going down. And it's a big N for Nadaski. Yeah. Use a parametric equation to limit it here and here. We get a pretty good N. Yeah. We're going to do all kinds of cool graphs where you could kind of like spell your own name. Quentin's going to be a little tough. You would need an ellipse and a straight line, right, to get your Q. A U could be a parabola. We're going to talk about the E, actually. In fact, we're going to do one right now. That could be an E. It just wouldn't be a function. You have to rotate the graph, right? But you could do, it would look like it even when we're done. But yeah, all kinds of cool stuff that nerds could do with graphs. I've just never taken the time to do it because I'm not that big of a nerd, for the record. All right, let's take a look at one. We're starting to understand the processes here, how we can use first and second derivatives to graph. I mean, that's a pretty accurate graph right there, actually. Right? That's fairly accurate and took almost no time. Write this one down. One last problem. Squeeze it in here. H of x is equal to x to the fourth minus 2x squared plus 5. Spent too long talking about physics earlier. All right. H of x equals x to the fourth minus 2x squared plus 5. What do we do first, Quentin?
Set f prime to, well, h prime of x is 0.
Set h prime of x, whatever it is, equal to 0. What is h prime of x, Jamie?
Is it 4x cubed minus 4x?
Okay, and so